Hello ib1 students, this is last revision lesson before your major test in next week. In next week you will write major in thermal physics. Yesterday I gave you one page with exercises to solve. Today I'm going to give you solutions. I hope that you did this. So please open your notebooks with your exercises, take pen, pencil, and watch carefully step by step and try and check your exercises. You can mark and check finally your score. Okay, so let's start with multiple choice questions. Okay, so let's take first two because the data, the graph is related with first two questions. Okay, so we have a substance, so we'll just hit it up at constant rate of energy transfer. Graph of its temperature against time is shown below. Okay, so we have 5 regions, and y-axis is temperature, on x-axis is time. And the question is, first question, which regions of the graph corresponds to the substance existing in mixture of two phases? Of course, it's easy. Two phases, so during probably melting and during probably boiling. So regions LM and NO, LM and NO, so answer B is correct. Exercise number 2. In which region of the graph is the specific heat capacity of the substance greatest? Remember that specific heat capacity is defined as amount of heat which is needed to increase the temperature of 1 kilogram of substance by 1 Kelvin. The greatest means that we have the rate of Q over T the biggest possible. Let's look what do we have on the axis. On one axis we have temperature, on other axis we have a time. So time means is related with the rate of delivering of the energy. So let's look. We have 3 other regions: KL, MN, and OP. Okay, so let's focus maybe at the beginning on OP. We have small change in temperature in long time, okay, which means that a lot of energy is needed to change the temperature. So probably this is correct answer. Let's compare this with, let's say, MN region. We have short time and huge change of temperature, which means that small amount of energy is needed to do this. Okay, so correct answer is region OP because a lot of energy is needed to change the temperature by small amount. So a lot of energy is needed, huge numerator, by change the temperature of small amount, small denominator. So the biggest C is in the region of OP. So correct answer for exercise number 2 is D. Okay, exercise number 3 and 4. Let me copy and paste. Okay, so exercise number 3. When a volume of gas is isothermally compressed to a smaller volume, the pressure exerted by the gas on the container walls increases. The best microscopic explanation for this pressure increase is that at the smaller volume, and we have 4 possibilities. Important here is isothermally. Temperature doesn't change. Temperature doesn't change means that molecules do not move faster. Okay, so let's check one by one. The individual gas molecules are compressed. Of course, this is not true. Molecules cannot be compressed. The gas can be compressed, but not molecules. B. The gas molecules repel each other more strongly. It's also not true because this is not the reason of increasing the pressure. C. The average velocity of gas molecules hitting the walls is greater. This is not true because temperature is constant, so there must be D. The frequency of collisions with the gas molecules with the walls is greater, and of course this is correct answer. Let's look. In smaller volume, molecules collide with the walls of the container more frequent, which means that we have more collisions, so in average bigger force acting on the walls, so in average bigger the pressure. Okay, so answer D. Okay, and exercise number 4. Lead bullet is fired into an iron plate where it deforms and stops. As a result, the temperature of the lead increases by an amount of delta T. For an identical bullet hitting the plate with twice the speed, what is the best estimate of the temperature increase? Okay, twice the speed. Twice the speed means that kinetic energy of the bullet is 4 times bigger, mv squared. Okay, so kinetic energy of the bullet is 4 times bigger. So if all kinetic energy is converted into heat, then heat which is transferred to the bullet is 4 times bigger. Heat is specific heat capacity times mass times delta T. This is lead, mass of the bullet doesn't change, so if Q is 4 times bigger, then delta T is also 4 times bigger, so correct answer is D. Okay, I hope that these first 4 exercises were not too challenging, so let's check next. Exercise number 5, together 11 points. It's rare. Okay, let me change slide for new one, paste it and check. In winter, in some countries, the water in swimming pool needs to be heated. Estimate the cost of heating the water in a typical swimming pool from 5 degrees Celsius to suitable temperature for swimming. You may choose to consider any reasonable size of pool. Clearly show any estimated values. The following information will be useful with specific heat capacity of water, density of water, and cost per 1 kilowatt hour of electrical energy is 10 American cents. Okay, and estimated values and calculations. So first of all, we have to estimate the size of the swimming pool. It's written typical swimming pool, so we can take 25 meters long a swimming pool. Okay. Let's take the size of swimming pool as 25 meters. The second dimension is 10 meters, and depth is in one side it can be 1.5, in second it can be 1, in second it can be 2, so around 1.5 meters. Okay, and let's assume, so this is first assumption, dimensions of swimming pool. Second assumption is that swimming pool is filled by water at all. Okay, so we can calculate the volume of water in swimming pool. This is 25 times 10 times 1.5. So we can calculate this volume. So it's 250 times 1.5, which results in 375 meters cubed. Okay, and next assumption. So still we are doing estimated values. Next assumption is suitable temperature for swimming. I don't know what is a suitable temperature for swimming. Of course, I know. We can take 22 degrees Celsius or 25. It will be easier to calculate. But finally, you can use calculator. So let's state that temperature of the water suitable for swimming is 22 degrees Celsius. So what is the change of the temperature? The water must be heated up from 5 degrees Celsius to 22, so by 17 degrees Celsius. This is our next assumption. Okay, so I think that's all. Of course, another assumption is that this heating system delivers energy directly to the water and no energy is lost. So let's look, because normally water evaporates. Our assumption is that this water doesn't evaporate. Another assumption that also walls of the swimming pool are heated up. In my assumption is that the walls are not heated up, that only water takes this thermal energy from the heating system. Okay, so calculations. What we have to find the cost of heating of the water. So first of all, calculate amount of energy, thermal energy needed to do this. Amount of thermal energy needed to do this is specific heat capacity times mass times delta T. Specific heat capacity is given as 4186 in standard units times mass. Okay, mass of water is not given directly, but mass is density times volume. So both and density and volume are given. Density is 1000 kilograms per meter cubed, and volume is here 375 meters cubed, so standard units, I'm not writing units, so this is 3.75 times 10 to the power of 1, 2, 3, 4, 5 times 10 to the power of 5 of kilograms. Okay, so we have 4186 times 3.75 times 10 to the power of 5 times change of temperature with estimated change of temperature as 17 degrees Celsius, so times 17, which results in, let me use calculator, 4186 times 3.75 times 17 and times 10 to the power of 5, so finally it is 2.67, in my case it's 2.67 times 10 to the power of 10 meters cubed, of course not meters cubed, of joules. Okay, so this amount of energy is needed in the form of thermal energy to heat up this amount of water by this temperature difference. Of course, if you have other result, which is the consequence of using another estimations, it's also correct. Of course, only if your estimations sense. Okay. So next we know that the cost of 1 kilowatt hour here is 10 American cents. So first of all, what is 1 kilowatt hour? 1 kilowatt hour is the unit of energy or heat. Okay, and it corresponds with 1 kilo is 10 to the power of 3. Watt is watt, and hour contains 3600 seconds. Okay, so finally in standard units we have 3.6 times 10 to the power of 6 of joules. And now we can use simple proportion. If 1 kilowatt hour is 3.6 times 10 to the power of 6 of joules, then how many kilowatt hours is 2.67, something we are looking for, times 10 to the power of 10 of joules. Okay, so finally we have to divide this by this, so our x, so energy expressed in kilowatt hours, is 2.67 times 10 to the power of 10 divided by 3.6 times 10 to the power of 6. Okay, so 2.67 times 2.67 times 10 to the power of 10, I'm using calculator, divided by 3.6 times 10 to the power of 6, which is 7.42 times 10 to the power of 3. 7.42 times 10 to the power of 3. And this is, this is energy, but in kilowatt hours. And last, we know that 1 kilowatt hour, the cost of 1 kilowatt hour is 0.1 American dollar. So total cost will be number of kilowatt hours times cost of 1. So finally is 7.42 times 10 to the power of 2, or 742 American dollars. So this is the cost of electricity needed to heat up water in this my imaginary swimming pool by 17 degrees Celsius, because I've assumed dimensions of the swimming pool and final temperature of water. Oof. Next. Okay, so new slide, and let me copy next one. Exercise number. This is still the same exercise, number B. Oh. Okay. An electrical heater for swimming pools has the following information written on its side. 50 Hz, 2.3 kilowatts. Estimate how many days it will take this heater to heat the water in the swimming pool. Okay, so we have to use equation for power, because this data is of course a power of heating system. So power is energy over time. We are looking for time, so this is thermal energy divided by power, and thermal energy was 2.67 times 10 to the power of 10, 267 times 10 to the power of 10 in joules. divided by power, which is 2.3 kilowatts, so 2.3 times 10 to the power of 3, so 2.67 times 10 to the power of 10 divided by 2.3 times 10 to the power of 3 is 1.16 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. 10 to the power of 7 seconds. Question is about number of days. So we can calculate number of seconds in 1 day. So let's write this T1. Number of seconds in 1 day is 24 times 3600, which is 86,400. So now we can calculate number of days by dividing 1.16 times 10 to the power of 7 by this 86,400, which is 1.16 times 10 to the power of 7 divided by 86,400. 134 days. Oh, nice time. Okay, so in my imaginary swimming pool we have to wait 134 days. And suggest two reasons why this can only be an approximation. Of course, first reason, I was talking about this, water, normally water evaporates, so this time should be different due to the evaporation effect. And second, we've assumed that all energy which is produced by the heater is transferred to the water in the form of thermal energy, so we have no energy which is lost. Okay, so classical answer for estimation. Okay, so next exercise. Exercise number 6. Okay, a cylinder fitted with a piston contains 0.23 moles of helium gas. The following data are available. We know volume in meters cubed, we have pressure in pascals, and we have temperature, which is 290 kelvins. I hope that this pressure is 10 to the power of 5. Yes, it is 10 to the power of 5. Okay, so I'm going to write that this is 1 times 10 to the power of 5 of pascals. Okay, and we have to use this data to calculate the value for the universal gas constant. Classical Clapeyron equation, PV equals nRT. We are looking for R, so this is PV over NT. We know P is 10 to the power of 5. We know V is 5.2 times 10 to the power of, I hope it's minus 3. Let me check again. Yes, it's minus 3. We know N, number of moles, 0.23, and we know temperature is 290 kelvins. All you have to do is use calculator. So 10 to the power of 5 times 5.2 times 10 to the power of minus 3, and all is divided by 0.23 multiplied by 290. Finally, I have 7.8. Okay, the question is about value. You don't need to write unit. Okay, so due to this data, the value is 7.8. Okay, state the assumption made in these calculations. My assumption was that this gas behaves as an ideal gas because this equation works only with ideal gases. So the assumption is that it behaves as an ideal gas. Okay, but this gas constant is a little bit different. Let me check again. Numbers 23. Okay, due to this data, I have result like this. Again on the calculator, 5.2 divided by 23 and 29. Yeah, 7.8. Okay. And exercise number 7. Okay, oh my god, a lot of, so let cut it here. Maybe let's do first 3 ABC. Okay, this question is about determining the specific latent heat of fusion of ice. Student determines the specific latent heat of fusion of ice at home. She takes some ice from the freezer, measures its mass and mixes it with a known mass of water in an insulating jug. She stirrs until all the ice has melted and measures the final temperature of the mixture. She also measured the temperature in the freezer and the initial temperature of the water. She records her measurements as follows. So we have mass of ice used, initial temperature of ice, initial mass of water, initial temperature of water, final temperature of mixture. But I don't see this symbol. This is TF, final, okay? And the specific heat capacities of water and ice are given. For water is 4.2 kilojoules and for ice is 2.1 kilojoules. Set up the appropriate equation representing energy transfers during the process of coming to thermal equilibrium that will enable her to solve for the specific latent heat of ice. Insert values into the equation from the data above, but do not solve the equation. Okay, so let's look. We have nothing about this jug, so we can assume that the jug doesn't take, is written in insulating jug, so it doesn't take energy from the system. So we have classical heat transfer. So one substance loses energy, another takes it. So we have Q, which is lost by water, is the same as Q, which is taken by ice. But this Q taken by ice can be split into 3 parts. Okay, first, increasing the temperature of ice, let's name it Q1. Second, melting the ice, Q2. And third, increasing the temperature of water from ice. Okay, so let's use these symbols, and in the next step let's use the data. Okay, so Q lost by water. Do we have amount of water in the jug? Student determines the specific latent heat of fusion of ice. Initial mass of water, yes, it's here. Okay, so this is specific heat capacity of water times mass of water times delta T of water is equal to specific heat capacity of ice times mass of ice times delta T of ice, next process of melting, specific latent heat of fusion times mass of ice, and increasing the temperature of water from ice. So we have water, so specific heat capacity of water. Water from ice has the same mass as ice at the beginning, and delta T of water from ice VI, and put data. So we have 4.2 times 10 to the power of 3, remember about this kilo, kilo represents 10 to the power of 3, times mass of water, which is initial mass of water 0.40, times changed the temperature of water. Temperature of water changes from 22 to 15, so by 7, is equal of ice 2.1 times 10 to the power of 3, mass of ice 0.12 kilograms, and change temperature of ice. Ice changes temperature from minus 12 to 0 to its melting point, so by 12. Next we have latent heat, which is unknown, and mass of ice, which is 0.12, and finally we have specific heat capacity of water, so 4.2 times 10 to the power of 3, times mass of ice, which is 0.12, times change the temperature of water from ice. Initially water from ice has 0 and finally 15, so from 0 to 15 by 15. Oof! So we have. Okay, B. Explain the physical meaning of each energy transfer term in your equation, but do not each symbol. Okay, so something I was talking about. So first, this is the thermal energy which is lost by water. Second, this is thermal energy which is gained by ice to change the temperature to its melting point. This one is thermal energy needed to melt the ice, and this one is thermal energy needed to increase the temperature of water from ice from 0 to 15 degrees Celsius. Okay, C. State an assumption you have made about the experiment in setting up your equation in A. Okay, so I've assumed that no thermal energy is lost due to the surroundings, so all energy which is lost by water is transferred in the form of heat to the ice. Okay? D, what do we have? We have still D and E. Okay, so let's place it here. Okay, so D, by using violet. Why should she take the temperature of the mixture immediately after all the ice has melted? Of course, remember, water evaporates, okay? So if she will wait longer, or then water will evaporate. Or another reason is that, let's look, probably the temperature of water with ice together is less than temperature of the surroundings. So if she will wait a long time, then this mixture will take thermal energy from the surroundings, which will change the temperature of the mixture. Okay, and E, explain from the microscopic point of view in terms of molecular behavior why the temperature of the ice does not increase whilst melting. Okay, it's a nice question. What happens during melting? In general, we have, in the case of solid, two types of energies in the particles. Kinetic energy, which is related with temperature, and potential energy, which is related with interaction or distance between molecules. Okay? So when temperature changes, then mostly kinetic energy changes. But during melting, we have constant temperature. So this is important. During melting, there is a constant temperature. So if there is a constant temperature, then kinetic energy of the molecules stays the same, doesn't change. So when energy is delivered, okay, to melt the ice, then this energy is converted to potential energy of molecules, which increases. Basically, bonds are broken and ice starts to be a water. Okay, because we have different potential energy. So difference between ice at 0 and water at 0 is not the difference in kinetic energy of the molecules, because average kinetic energy of the molecules must be the same because temperature is the same. So difference must be in potential energy. So to melt the ice, we need external energy, and this energy increases potential energy. Okay, so what happens? Potential energy increases, so bonds are broken, and ice is converted into water. And this is something which is known as a melting. Okay, probably it was the last one. Yes, it was the last one. So exercises were not difficult. You can, as you know, this chapter is probably the easiest one. In my opinion, is the easiest one. One of the shortest and the easiest. Next week you have a test. I'm not going to give you two tests, multiple choice questions and open questions. It will be in the form of one paper, one test. I don't know the form, one PDF file, maybe for 60 or 70 minutes. The slot will be 2 hours long, so at this time you have to print it, solve, scan or take a photo, merge into one PDF file, and attach as assignment in Google Classroom. If you have any questions, write to me in the form of post below this movie. If you have any problems related with thermal physics, ask me again, or by post in Google Classroom or by writing private email. So good luck in learning, learn physics, stay at home, and see you. Bye.